Howdy!
I'm Elisha Foster.
I'm Russell Haley.
I'm Quinn Manley.
And I'm Ryan Moore, and we are a senior electrical engineering team at Texas A&M working on Project DOA, Direction of Arrival.
We'll be explaining our senior Capstone project, as well as each subsystem involved.
The first thing to mention is that this is a research project in collaboration with Dr. Huff and Dr. Chamberlain's Innovation Laboratory.
The purpose of this project is to provide a highly accurate method of indoor tracking.
The current tracking system, GPS, works well outdoors, but is insufficiently accurate indoors. We seek to provide tracking of an active beacon with an antenna array, a network analyzer, and a backend server.
The polarization of each antenna in the array can be set via an Android app, which communicates with an embedded control system.
Once set, the server can then be notified and then can begin polarization checking on the antennas and then can gather data on the active beacon signal. Once enough data is received, the server can then run calculations to determine the most likely location of the beacon.
We'll now briefly explain each subsystem. Hi again, I'm Elisha. I'm in charge of the phone interface system. It is the user interface for our system.
And I'm Ryan Moore, and I am in charge of the control subsystem.
Within this GUI, the user can change each antenna's polarization with a tap and can change between two different antenna array configurations. The phone communicates to the control subsystem over Bluetooth when the send button is pressed.
The purpose of the control system is to read the data from the phone app, change individual antenna polarizations based on this data, and control which antenna the server is polling for the beacon signal. To explain how the subsystem works, I have created a graphical overview to easily convey the intricacies. Here the viewer can see the whole subsystem. The control subsystem has been divided into 3 systems to allow for greater efficiency, modularity, and ease of coding. In the first system, we have the phone communicating with the master Arduino, which receives, decodes, and processes the data sent to determine what needs to occur. The master then communicates instructions to the other 2 systems over an I2C bus. The second system controls the polarization switching. This system outputs the data received by the first slave to the shift registers, which controls how each antenna is polarized through voltage biasing. The last system is the antenna connection switching. The network analyzer being used can only be connected to one antenna on the array at a time. So we switch between each antenna using the second slave so the server can receive the correct information from all the antennas. As the viewer could see, the control subsystem is very complicated, so I have chosen to present 2 of the control systems working alongside Elisha's phone app. Here we have the master and the slave that controls the polarization switching. For ease of understanding, I have attached LEDs to represent 5 antennas' polarizations. The green LED represents vertical polarization and the red signifies horizontal polarization. From top to bottom, we have antennas 18, 13, 10, 7, and 4 represented.
Here I will send the all vertical configuration and all the green lights will light up. Now I will send the all horizontal configuration and all the red lights will light up. Now I will change only antennas 4, 7, and 10 back to vertical, meaning the bottom 3 sets should be all lit green.
Hi again, I'm Quinn Manley, and I'm in charge of the antenna subsystem. More specifically, I work on the design and fabrication of the antennas.
The antenna we have is a cross-dipole structure with diodes across the gaps. One set of diodes are forward biased, and the other set are reverse biased. This allows us to decide which arm conducts based on a biasing voltage we apply. Here we can see that no biasing voltage is applied and the VSWR reflects that. Here we have a positive biasing voltage applied and the VSWR shows that one of the arms is conducting. If we applied a negative biasing voltage, the other arm would conduct. This is how polarization switching is achieved.
Hello again. I am Russell Haley, in charge of the data acquisition and algorithmic side on the backend server. We configure the field fox for a 3-sample sweep centered on 2.45 GHz with 0 sweep length. The value returned is unwrapped phase. 2 of the data points are discarded, returning a single sample. The samples are used to derive a phasor representation of the received signal at each antenna. This is called the vector x. The eigenvectors of XX conjugate define the noise subspace. These eigenvectors can be used to calculate a pseudospectrum. Thus, where E sub n is a matrix with the eigenvectors as its columns, and A of theta phi is a vector coupling coefficient obtained for each antenna from the dot product of a unit propagation vector with the location of that antenna in space. The maxima of this function, in the theta phi plane, are the propagation vectors of the incident signals. The algorithm will be implemented using SciPy.
This concludes our video presentation. We hope you've enjoyed seeing what our project can do so far.
Thanks and gig 'em!